So if we go back to where we were on Monday we ended with this overall idea of classification. Just can we put our compounds into groups? And we focused primarily on the ionic group versus the molecular group and trying to recognize what differences there were between those two groups so that we could identify and start to try to figure out how to name them. Now, the primary purpose of today is to focus exclusively on ionic compounds. Now, of the naming systems that exist, the ion nomenclature system is probably the most difficult because it's the most diverse. Overall, ionic compounds can be identified because we can identify positive and negative ions in them. And if you remember from Monday, the thing I focused on primarily was metals and nonmetals. If I see metals and nonmetals in the same compound, I know I'm dealing with an ionic compound of some kind. The thing that holds these compounds together are charges. In particular, the attractive charges that exist between positive and negative ions. And so in particular, there are 4 common forms of an ionic compound. The first is the most simple. I've got a metal and a nonmetal. Metal ions are positive in charge. Non-metal ions are negative in charge. I stick them together, I've got an ionic compound. The second form is also relatively common, and I noticed a typo here. Metallic ions are positive in charge, not negative. But I have metallic ions and polyatomic anions. That's another form of an ionic compound. Now, polyatomic ions we introduced kind of in form on Friday. And I showed you there's that relatively large list of ions that fall into this category, where I've got multiple atoms together and they collectively have a charge, usually negative. The other 2 forms are basically the same, only they focus on ammonium ion. And the reason we pull out ammonium ion specifically is ammonium ion, NH4 positive, is the only polyatomic ion that has a positive charge. And so that ammonium ion and its positive charge can interact with nonmetals, or it can interact with other polyatomic ions. Now, when it comes to ionic compounds, there is a little bit of terminology here that is different. With molecular compounds, we focus on the idea of a molecule. So a molecule being kind of the smallest unit of a compound. With ionic compounds, we don't call them molecules because they don't really exist individually. You see, ionic compounds form these 3D crystal lattices. And so what happens is you've got these ions that are attracted to a whole bunch of negative ions and a whole bunch of positive ions all together to make this big crystal. So because of that, it's really hard to pick out an individual molecule of a given ionic compound because it's part of this big, vast array of molecules. So what we do instead is we focus with ionic compounds on something called a formula unit. And a formula unit is basically just a fancy way of saying kind of the smallest repeating unit inside of that crystal. So if I have sodium chloride, for example, I've got a bunch of sodium ions and a bunch of chloride ions all alternating throughout this crystal in 3 dimensions. So it's not just positive, negative, positive, negative, positive, negative, side to side. It's also positive and negative, up and down, and positive, negative, front to back. So you can see at the molecular level, this is a pretty complex substance. And so because of that, you can't really isolate, okay, well, this is sodium chloride, this is a molecule of sodium chloride, because it's associated with 6 other sodium chlorides. So we use formula unit instead. When it comes to naming these ionic compounds, a couple of things that we have to know, things that are always true. First of all, ionic compounds are always charge neutral. What we mean by that is that if I look at the sum of all of the positive charges, we call positive charges cations. If I look at the sum of all of those cations, and I compare them to the sum of all of the negative charges, we call those anions. So if I compare the sum of all of the cations and all of the anions, what I should get is that it is zero sum. Every single positive is matched by a negative. Just like we saw with isotopes and atoms. Every single proton was matched by a neutron or by an electron in a neutral atom. It's the same thing in ionic compounds. Every positive is matched by a negative. And that's a good thing, because that means that the formula for an ionic compound is kind of predictable if I know the charges of what make it up. All right, this is the process that your book gives you for how to write the formula of an ionic compound. And if this makes sense to you, great, more power to you. If this is as clear as mud, let's see if we can figure out a couple of ways to kind of make it a little bit easier to understand. So the first idea is relatively simple. If I'm writing the formula for an ionic compound, I need to know what makes it up. So I need to know what the positive ion is and what the negative ion is. Simple enough. From there, I'm going to do one of two things. If the ions match each other, then I know that they exist in a 1-to-1 ratio. And so I'm just going to write that out as 1-to-1. So, for example, I got magnesium oxide here on the right-hand side. Those 2 ions match each other in charge. And so instead of doing this, where I crisscross them and turn them into coefficients, or excuse me, into subscripts, I know that since they match, I'm going to write them as a 1-to-1. The correct formula for magnesium oxide is MgO. And it's that way because I can look at this and see, okay, if I put 1 magnesium and 1 oxide together, I'm going to have charge balance. I got 2 positives and 2 negatives. They're going to cancel each other out. Where this crisscross method is particularly useful for us is when the charges do not match. If the charges do not match, then you've got some math problems to do. And if you go back to those steps that I was showing you, that's what they're trying to explain to you about finding the lowest ratio and the least common multiple and a whole bunch of other math stuff. The reality here is simple. To get them to match up, the easiest thing to do is to take those charges and cross them over to make subscripts. So I've got aluminum and oxygen there. The aluminum's a 3+, the oxygen's a 2-. Obviously, they do not match up. If I put 1 with 1, I'm going to have a leftover positive charge, and I can't have that. To make the formula correct, I'm going to take the charge for the oxygen and make that the subscript of the aluminum. I'm going to take the charge of the aluminum and make that the subscript for the oxygen. That's what's called the crisscross method. Now, why does it work? Well, basically, it falls into what's called the lowest common multiple. Lowest common multiple between 2 and 3 is 6. And so if I have -2 times 3, that gives me -6. If I have aluminum times 2, that gives me +6. That's where my charge balance ultimately comes from. Again, we can kind of work it out with this crisscrossing and not actually have to do the math. I think you'll agree with me. Anytime we can avoid doing math unnecessarily, we're going to avoid doing math unnecessarily. So that's how we write formulas. Now, there's a big piece of that. I have to know what the ions are to write the formulas. So how do we go about doing that part of it? We can get a little bit of help from here. When it comes to naming ionic compounds, obviously the first step that we have to do is we have to identify it. We have to identify that it is ionic in the first place. And we already talked about a couple of ways to do that. First and foremost, if you can identify a metal and a non-metal in the compound, chances are really good we're talking about an ionic compound. If you can't, then you need to look for other signs. Are there polyatomic ions in there that you recognize? Does it have more than 3 elements in it? Another good sign that it's ionic. But the naming process is actually really simple if we get to that point where we identify it. The naming of any ionic compound is the same. I name the positive ion, I name the negative ion, I put them together. Positive's always first, negative's always last. I put them together to make one compound name. Like I said, the trick though, how do I name the ions in the first place? Well, let's start with the positive ions. Cations can be subclassified into 3 categories. There are the metal ions that have a consistent charge no matter what. And if that's the case, we just name them as the element that they are. Now, your book refers to these as invariant elements. Invariance is just a fancy way of saying they have a consistent charge. Where do we find these? Well, for the most part, these are in the main group. parts of the periodic table. So these are the alkali metals, these are the alkaline earth metals, these are your aluminum group metals, and so on. So mostly we're talking about the first two columns of the periodic table, but we can also talk about this third column, starting with boron, and there are also a couple of weird ones in here. So for example, let me show you on the periodic table where we can find these. It's actually really easy to identify. So if you have your periodic tables on you, this would be a good time to make a notation. All right, so in previous meetings, we've talked about how the alkali metals are always +1. We've talked about how the alkaline earth metals are +2. We've talked about how the boron group is generally +3. So those three groups fit into this first category. So if I have an ionic compound that has any of those metals in it, that's how I name it. So if it's got potassium ion in it, I just name the ion potassium. If it's got aluminum in it, I just name it as aluminum. The other exceptions, and this is kind of an odd group, if I draw a triangle starting at zinc and crossing over to cadmium and indium, those four transition metals also only carry one charge. And the charges they carry actually follow a pattern as well. So indium is going to be +3 because it is in this third group here. The zinc group, including cadmium, would be +2, and silver is +1. So if we see a metal from one of these series of groups, we automatically know what its charge is. And we know that from a naming standpoint, we just name it what it is. So ionic compounds containing cadmium are cadmium, and then whatever the ion is attached to it. Zinc compounds are zinc, and whatever is attached to the zinc. So that's the first group. The second group, there are metal ions that can have multiple possible charges. We find those in the transition metals. So it's a transition metal not in that triangle. It has multiple charges possible. How do I tell the difference between those charges? I use a Roman numeral. The Roman numeral tells me what charge it is. So, for example, if I've got iron 2+ here, the name of that ion is iron 2. And the 2 is represented by 2 in Roman numerals, II. Iron 3+ is iron 3, iron III. Vanadium 5+ is vanadium 5, vanadium V. So that's the second category. Here are the ions that have different charges. How do I tell the charges apart? I use a Roman numeral to help me tell, okay, this is iron 2 versus iron 3. This is vanadium 5 versus vanadium 1 versus vanadium 3. And then the last category is ammonium ion. Again, ammonium ion is the polyatomic ion that is positively charged, and we just call it what it is. It's ammonium. On the anion side, it's a little bit simpler. Basically, there are two forms. There are the standalone nonmetals, and all you do with those is you change the ending of that element's name to IDE. The charges on those follow the periodic table charges that we've discussed before. Halogens are -1, oxygen groups -2, nitrogen groups -3. But the naming itself is relatively easy. Oxygen becomes oxide, nitrogen becomes nitride, bromine becomes bromide, chlorine becomes chloride. So that's the first group. First group is just simply, I've got an element that has a negative charge, I just change its ending. The second group is a group of polyatomic ions that are negatively charged, and we just name them according to what we named the polyatomic ion. And just as a little bit of a hint, when we come up to that nomenclature quiz in that thing, those polyatomic ions you're going to have to know them. So make sure that you're spending some time working on getting more familiar with that list. So now we just put it together. To name an ionic compound, we put together the name of the cation and the name of the anion. So if I have a compound like KBr, I look at K, okay, K is an alkali metal, it is in the first group, it always is +1 in charge, so it's potassium. I look at Br, Br is an element by itself, bromine turns into bromide, the name of the compound, put them together, potassium bromide. The second example we have, I've got NH4. I have to recognize NH4 is ammonium. So the name of that ion is ammonium. The F is fluorine. So as an ion, it would be fluoride. Put the two together, it's ammonium fluoride. Third example, I have iron. I look at iron on the periodic table and say, oh, transition metal. I need to know its charge. Now, if I don't know what its charge is right away, I need to use the other information in the compound to help me. So one way I can do that is if I know I have multiple subscripts here, I can reverse those subscripts. So I talked earlier about the crisscross method. You can reverse the crisscross method to figure out charges. So that tells me that the iron's a +3 and the sulfur's a -2. And if I looked at the periodic table, I would see that sulfur is indeed a -2 because it's in the oxygen group. So I can work backwards from there and say, okay, if the iron is +3, that means it's iron 3. Sulfur is sulfide. Put it together, it's iron 3 sulfide. So that's the process. That's the process that has to come about. Now, how do we put it into action? And so basically the rest of the time here, it's practice problems and trying to get better, trying to get more familiar with that. So let's take a look at our first set of practice problems. Okay, Ca. What is Ca? It's calcium. Okay, calcium is not a transition metal, so we can just name it as it is. It's calcium, right? OH, you know your polyatomic ions, it's hydroxide. That's the hydroxide ion. So the name of this compound is calcium hydroxide. Might not be a bad idea as you're working through these examples, as you're working through your homework, until you get more familiar with that polyatomic ion list. Have that open somewhere where you can access it really quickly and easily, so that you're not constantly searching through it. These are things that with time and with usage, they do become more familiar. All right, let's look at the second one here. Cr is chromium. But I gotta look at the periodic table, and I look, okay, chromium's element number 24. It's a transition metal. So I can't just stop at chromium. I need to know its charge. I also need to know what SO4 is. SO4 is sulfate. And if I look at my polyatomic ion list, SO4 has a -2 charge. So if SO4 has a -2 charge, what's the charge on my chromium? How many chromiums do I have? I have one, right? So if I only have one of the metal, it must match the non-metal. So the non-metal is -2. That must mean that the chromium is +2. If chromium is +2, that means that the Roman numeral is 2. So this is chromium 2 sulfate. Right. Questions with this example? Oh, okay, so calcium has a charge of +2. Now hydroxide is OH negative, because it's oxygen and hydrogen together. And so from that standpoint, if you're looking at the charges, you've got a -2 oxygen and a +1 hydrogen. -2 + 1 gives you -1, which is why the hydroxide is a -1 charge. So this formula is the way that it is. Since I have unlike charges, a 2 and a 1, I've got to switch them to get the correct formula. And so that means I need 1 calcium, which is shown, and I need 2 of the hydroxide, which is why the 2 is on the outside there. So when we have polyatomic ions, we always put polyatomic ions in parentheses when we put subscripts on them, so that we don't confuse the issue. If I put just a 2 on the outside here without the parentheses, it would be water. H2O. That wouldn't make any sense for this context. So since they have the same charge, then we don't need subscripts. So if the charges match, we don't need subscripts. The only subscript here is this 4 4, and that's because that's part of what makes it sulfate. If it wasn't 4, if it was 3, it wouldn't be sulfate anymore, it'd be sulfite. Different compound, completely different eye. Good questions, though. Other questions? All right, let's take a look at another couple of examples. All right, in this case, we have to identify, we've got 2 different polyatomic ions. We've got NH4 and we've got NO2. NH4 is a +1, NO2 is a -1, so we can see that charges are equal, so we don't need further subscripts. What is this compound? Well, NH4 is ammonium. NO2 is nitrite. So the name of this compound is ammonium nitrite. For this last one, we have Pb. Pb is lead. Lead, although lead is not in the middle of the table, it is considered a transition metal because we basically consider any metal that isn't in the first 2 groups or the 3rd group to be a transition metal if it is before that staggered staircase. So tin, lead, antimony, bismuth, polonium, those are all considered transition metals, even though they're not in that middle block. Same thing for any of the metals in that bottom block of the periodic table here, the lanthanides and the actinides. Those are considered transition metals as well. So I know I have lead. Lead has a multiple charges possible. So I'm going to need to stop before I name the rest of it. S is sulfide. Now, if I look at the periodic table, I see sulfur is in oxygen's group, so it has a -2 charge. And I can see from the subscript that there are 2 of them. That means that the total negative charge is -4. So what does that tell me about the charge on the lead? I know it has to be positive. How positive is it? Well, how negative is it matching? It has to match -4. Only one of them. So it's got to be +4 to match. So in this case, the lead is +4. Roman numeral for 4 is IV. So lead 4 sulfide, lead IV sulfide is the appropriate and correct answer there. Any questions with these examples here? All right, I want you to try this one out and then actually on second thought, you're going to play practice in the homework. Let's talk about reversing it. Part of nomenclature is you have to be able to go both ways. So past couple of examples, we've been taking formulas and turning them into names. How do we turn the names into formulas? And basically the answer is kind of what we were talking about at the very beginning of this process. What are the ions? How do the ions interact? So in a lot of ways, this can be easier if we're able to identify what the ions actually are. So for example, iron 3 chloride. We know that iron 3 chloride is going to have an iron 3 ion on it. That's Fe plus 3. Remember, the 3 there tells us the charge on the iron. For chloride, I know I'm dealing with chlorine, Cl. I look to the periodic table. Periodic table says chlorine's a halogen. All halogens are -1 in charge. So now I ask myself the fundamental question. Do those charges match? No. If they don't match, then we cross them to get the correct formula. The correct formula would be FeCl3. Iron has a charge of 1 coming from the, or excuse me, has a subscript of 1 coming from the chlorine. Chlorine has a subscript of 3 coming from the iron. For magnesium sulfate, I looked at the periodic table. Magnesium, +2 in charge. It is not a transition metal, so I don't need to worry about a Roman numeral. And the fact that I wasn't given a Roman numeral tells me that it doesn't have other charges to consider. I go directly to the periodic table to figure out what its charge is. Sulfate is a polyatomic ion. SO4 -2 is its formula. Do the charges match? Yeah, +2, -2, they match. So I don't need to do any crisscrossing. I just rewrite the formula as a 1-to-1 fashion. All right, let's take a look at one more set of examples and then we'll call it a day. What is the formula for copper 1 oxide? For copper 1, so copper is Cu. 1 tells us that's a 1 positive charge. Oxide is O. I looked at the oxygen group, I see, oh, -2 charge. Do the charges match? Nope. So we cross. Copper gets a subscript of 2 from the oxygen. Oxygen gets a subscript of 1 from the copper. Subscripts of 1 we just leave alone. Cu2O is the correct formula for this oxide. Last example, iron 3 carbonate. Iron 3 would be iron 3 plus. Carbonate would be CO3 -2. Do the charges match? No. So cross we shall. Iron gets a subscript of 2 from the carbonate. Carbonate gets put in parentheses and a subscript of 3 from the iron. Fe2CO3 taken 3 times is the correct formula. So in this homework assignment that's due tomorrow night, you're going to see a lot more of these kinds of examples. Some of them are going to be a little bit easier than others. It just depends upon your level of comfort. What I would tell you, though, is if you don't have your polyatomic ions memorized yet, which I'm going to assume most of you don't, that's going to be something you're going to want to have close at hand so that you know the formulas and the charges to make it a little bit easier to work through those. That's due tomorrow night. Quiz 5 prep and mastering is there for your practice to get ready for Friday's quiz. If you have not submitted the checkpoint, go ahead and do so. Have a great day.